Hi everyone, welcome back. In this video, I'll introduce the envelope theorem using one simple utility maximization example. First, I'll solve it using the given functional form and then I'll derive the result generically. The key idea is that the Lagrange multiplier measures how the maximum value of the objective function changes when the constraints shift. Okay, suppose we have this optimization problem. We want to maximize utility subject to a budget constraint, and we form the Lagrange as such. And the first thing that we have to do is that we have to take the derivative of L with respect to x, and we have to put it equals to a 0. So the partial derivative of u with respect to x, and then we have a minus lambda px is equals to a 0. So the first equation that we have is this. I'll just make a box here so we remember this. It'll come in handy. And suppose the utility function is given, then we can actually take the derivative as well. So let's just take the derivative. We'll get alpha x alpha minus 1 y beta is equals to lambda px. So essentially both of them are the same equation. Okay, moving forward, the second first order condition that we have to take is the derivative with respect to y, which is going to be the partial derivative with respect to y of the utility function, and then lambda py is equals to a 0. Again, this becomes the derivative of u with respect to y is equals to lambda py. So I've written this generically, but if the functional form of the equation is given, then this will become a beta. Where was the utility function? Yeah, there it is. We have a beta x alpha y beta minus a 1 is equals to lambda px. So this is the second equation that we've obtained. Okay, from these two, we're going to assume that a lambda is actually not equals to a 0. Therefore, we have a constraint which is binding. So a binding constraint, actually I should write binding first. So a binding constraint means in this case that the budget, the person is going to, the optimal bundle is going to lie on the budget line. So he's exhausting all of his income. Okay, so if lambda is non-zero, then from the first and the second equation, so from the first and the second stationary condition, we get the value of lambda. From the first, we get a derivative of u with respect to x over px, and from the second, we get the derivative of u with respect to y over a py. Why did I put px here? Oh, that's just a silly mistake. Oh, why? A very lethal silly mistake, actually. But I'll make the correction. We're all human. Okay, and this basically is, and we already wrote that, it's an alpha x alpha minus 1 y beta over a px, and this is a beta x alpha y beta minus 1 over a py. So this kind of looks familiar. This is going to actually give us a tangency condition, which was the slope of the budget line should equal the slope of the indifference curve. So moving forward, we have this equation, and this becomes px over a py is equals to beta x alpha y beta minus 1 over n alpha x alpha minus 1 y beta. So therefore we are left with beta y and alpha x. And this is essentially the tangency condition that we usually actually study in a first year economics course. This is the condition, tangency condition, which says the slope of the budget line, which is px over py, should equal the marginal rate of substitution. Okay, so if this is the tangency condition, we're going to put it in the budget constraint right here, and then we'll have the optimal values of x and y. So you can make anything the subject. So let's make y the subject from here. Y is equals to alpha px over beta py into x, and now we can substitute it in the budget constraint. So we're solving them simultaneously. I'm doing this just as a recap because this is what the budget line looks like. This is what the indifference curve looks like, and I'm basically solving them simultaneously because I need these optimal values of x star and y star right here, which this being my indifference curve. Anyhow, so when we solve it simultaneously, I'll get pxx plus py alpha px over beta py. As you can see, this kind of very nicely cancels out the py here. So the py goes, and I can take x the subject because x comes here and here as well. So I have a p, actually I can take px out as common, pxx as common. I have a 1 plus alpha over a beta income, and therefore that's my optimal value of x. So which is going to be the beta should go over, beta should go like that, alpha plus beta should go down, and m should get divided by a px. So that's my optimal level of x, and therefore through this we can find the optimal value of y. So the optimal value of y is just going to be alpha px beta py into x star, and we just found out what x star was. I can bring it down, and as you can see, px nicely gets eliminated, beta goes away, sort of like a very symmetrical reflective kind of. So we have, if there was a beta, there's an alpha here, alpha plus beta appears in both the denominators, the income appears in both, and we have a py here. So remember, this is the optimal level of x, this is the optimal level of y, and therefore what is the maximum value function? So the maximum utility is going to be achieved when you plug in these values in the utility function, and we call this the maximum value function. This is going to be known as the maximum value function. Okay, let's find it. It's usually denoted by V, and the answer is going to be in terms of prices and income. So we can just say it's a function of income, because later I need the derivative just with respect to income. And it's basically just the objective function at its optimal maximized value. So the objective function in our example was x power alpha, and for y it was y power beta. So we are just going to plug in the optimal values that we've calculated. So this was the value of the optimal x, and a very similar kind of expression for y. This is, I think there was an alpha here and a py here, and we had a beta here. So this is the optimal level of the maximum value of the function. Okay, so for simplicity, let's just assume that the value of alpha and beta is equals to a 1. I'm just doing this for simplicity because right now it's going to be very hard for me to take the derivative with respect to m, because I'll have to employ the product rule, because m comes here and m comes there. So let's just make life easy for ourselves and assume that the production function that we wrote as x power alpha and y power beta is just simply x into y. Which basically makes things easier for us, because my optimal value of x simply becomes, actually we don't need to do this, 1 plus 1, so it's a 1 over 2. So it's just going to be m over a 2 px, and y star is a m over a 2 py. And once we plug these two into the utility function above, we'll get m over 2 px power alpha, which was now a 1, and we'll have a m over 2 py power beta, which is now an 1. So the maximum value function is just a m square over a 4 into px py. So this is now this is where the fun begins. Actually, one thing we're going to notice is that we're going to take the derivative of the maximum value function with respect to income. So basically we're saying, what happens to his optimal consumption if his income rises, or what happens to his optimal consumption if income falls. So we are basically relaxing the constraint. And when we take the derivative with respect to income, we are going to get an m, and 2 2s are 4, so we get a 2 here, px py. Okay, and we want to see if this is equal to the value of the multiplier. So what was the multiplier? The multiplier was this. We can take any expression, actually. It doesn't matter actually which one. Let's just take this one, or just write this one here. So let's see if the value of the multiplier also is the same. Okay. This is the optimality condition, remember, that we got when we took the derivative. We took the first order condition. And I want to plug in, first we assume for simplicity that alpha and beta is equals to 1. So first let's plug that in. So we'll get an x power 0 and y power 1 is equals to lambda px, and then from over here we are going to get a lambda is equals to y over a px. Okay, so what is the value of lambda at the optimal point? Remember, this was the maximum value function, so we are observing the function at optimal values. So we have to see the value of lambda at the optimal level as well. So we have to plug in the optimal value of y and see what the answer comes. So the optimal value of y was a m over p to y, and this is and we're basically multiplying it with 1 over, or I'll just write it so nobody feels confused. I'm just writing it like this: y star multiplied by 1 over a px. Okay, and we get our final solution m over 2 px py. Can you see that the value of the multiplier at the optimal point is exactly the same as the derivative with respect to the objective function at the optimal point? What this means is that the multiplier basically tells us how the optimal consumption, or the optimal value of the objective function changes when you relax the constraint. So as a summary, I can write that the value of lambda at the optimal point is basically the derivative of the maximum value function at when we relax the constraint, or you can even write it as the derivative of utility at the maximum point when you take the derivative with respect to m. And you'll be surprised that if you take the derivative of the Lagrange at these optimal values, then again you're going to get the same answer, because the Lagrange actually collapses to the utility function when the budget constraint is satisfied, because this right here becomes a 0. Wait, this expression becomes 0. So L star and U star are actually the same. So the key takeaway from this is that the multiplier shows how the optimal value of the function changes when you relax the constraint. If but this question was fairly easy because of the fact that I had actually mentioned the functional forms. So if you've given a question in which you have to prove the envelope theorem using just the generic form, that's not actually that difficult either, because we're just going to follow the same thought process, which was that you take the derivative of L with respect to an x and you have to put it equals to a 0. So therefore in this case you take the derivative with respect to a g, and then k is a constant and you can only take the derivative of h with respect to an x. And once you put it equals to 0, you get the expression for the multiplier, which is going to be a derivative of g with respect to an x and derivative of h with respect to an x. Hence, the change in x cancels each other out, and we are left with the partial derivative of g with respect to h. So basically it's telling us it's the change in the optimal function when there's a change in the constraint. Okay, and it's going to, it should be equals to the change in the maximum value function when you relax the constraint. So when the value of k changes. Okay, then what did we do? We stated that since the multiplier is not equals to 0, complementary slackness that we discussed in the previous lesson about optimization was that if the multiplier is not equals to 0, then the associated constraint has to be equals to a 0. So in this case, it means that h of x has to be equals to k. Um, so when and then we're going to put this condition in the constraint and solve for x star. How do I write this down? I can say that this will and this solving simultaneously solve simultaneously to obtain the optimal value of x star. Okay, next point is that the maximum value of the function of the objective function is called v, and it depends on k, and it is just the value of the objective function at this optimal point. And remember, this optimal point is actually going to be dependent on the constraint, on the level of k. For instance, the previous example, the higher the income, the more you'll be able to afford more quantity of good x, right? So obviously your optimal bundle does depend on the amount of income that you have. So when we take the derivative of v with respect to k, we can take the derivative of g first with respect to x, and then the derivative of x with respect to k. And we can do a little bit of algebraic manipulation here by multiplying, dividing by the change in h. So for instance, if I first so that nobody is confused, I'm going to write this like this. Okay, dg over dk, dk x over dk, and suppose I multiply and divide by the change in h. And now suppose I switch, like I can write dg by dh, and I can actually bring dh inside dx. Actually, this doesn't need to be a partial, it can be x only depends on k, so it can be straight. Okay, so the value of we've just found out that the value of dg by dh is actually lambda, so we can write lambda here. But what about this expression? We need to figure out what this expression means. Okay, that's easy enough. So what was this? Like, we had this constraint, and once we put the optimal value inside, we're going to get this expression, right? So if I take the derivative with respect to k on the both sides of this equation, so this as well and this as well. So on the left hand side, I'm going to get the partial derivative of h with respect to x, and then x with respect to a k, because the answer of x does depend on k. And over here we get a 1. So we can substitute this value over here. And then what will we get? We had dv by dk as this. And now we can substitute in the value of 1, and therefore we get the required result, that the multiplier at the optimal point is simply the change in the maximum value function when the constraint is satisfied. Another way, which maybe a few of what you would probably find maybe easier than the above one, would be that we can also do this as follows, that just say that we find the optimal level of x, where we know that the optimal level is dependent on prices and income, right? So it is dependent on price. And when we substitute in all these optimal values, we'll get as follows. We'll get an L star here because we've substituted the optimal values. You got a U star here because we put in the optimal values. Then you have the optimal this, optimal this, optimal this. Okay, so what we can say is the derivative of L with respect to an income is going to be the derivative of a U with respect to an X. Then the derivative of X, remember it depends on income, with respect to M, then plus the partial derivative of U with respect to a Y, and then you have the derivative of Y with respect to M. And remember, the at the optimal value, the constraint is actually satisfied. But what we need to understand also is that M comes over here because X depends on M, and Y also depends on M, and lambda also depends on M. So because these are two things being multiplied together, we're going to have to use the product rule. So for instance, first of all I'll just keep lambda as it is, and I'll take the derivative of the inside expression with respect to income. So I know X star depends on, yeah, I should actually write we find, because these are two optimal values, so we find X star, Y star, where we know both of them will be a function of income. So we will be able to take the derivative with respect to income. So here we go, derivative of X star with respect to income minus by the derivative of a Y star with respect to income. Okay, and then the constraint as it is, and the derivative of the multiplier. So the derivative of the multiplier with respect to M, and this constraint as it is. And like I mentioned before, that the constraint is always satisfied, so this expression has to be equals to a 0. Okay, simplifying above, this is the derivative of U with respect to X, and then we have a derivative of X with respect to M. Then we have a derivative of U with respect to Y, derivative of Y with respect to M, plus lambda star minus lambda star px d star x over, all of them are star values. Okay, so like sometimes I forget to write it down. These are all optimal values. It's just sort of like, I don't know, just taken for granted, and sometimes I forget to write them down. Okay, so what can I take as common? I can take this as common with this, and I can take this common with this. So let's do that. I'll be left with a ux minus lambda px into derivative of optimal value of x with respect to income, and then I have a uy minus lambda py derivative of y star with respect to m, and then we have plus lambda star. So all of this part is this, including this right here, and this right here came over here, and this nice little guy came here. Does this look familiar, this equation? I'm going to scroll up and show you. In the first question, voila, do you see? These two things are actually equal to each other, which would mean this whole expression is actually equals to a 0. So at the optimal value, this expression right here is actually equals to a 0, and this is also equals to a 0. Therefore, our final answer is a lambda. So the derivative of L star over M, which I told you is the same as the derivative of the utility at when you relax the constraint, because when the budget is being when we have a binding constraint, when the budget is completely used, then this whole expression becomes 0. So the optimal value L star U star are the same. And this is called the derivative of the maximum value function with respect to M, which is now lambda as required. Okay, phew, this was long. Anyhow, this wraps up our quick look at the envelope theorem, a very powerful, and I find this a very beautiful result that shows how the maximum value of an optimization problem changes without differentiating the optimal choices themselves. I hope you benefited from this video, and I'll see you next time. Take care.